Hello students, good morning. Welcome to today's video of the GATE paper analysis. Hope all of you must have written, GATE mechanical students, you must have written the GATE examination well yesterday. Paper was went off up to 5:30 and I keep getting the questions based upon the memory based, because students based on their memory they keep sending me the questions. By the time I got the questions it was quite late, about it was 11 o'clock. Then I thought I would give the video today actually. In fact, based upon the feedback what I have received from the students which have written the GATE examination yesterday, the paper seems to be tough, moderate to tough. I will rate the paper as moderate to the tough, based upon the feedback what I have received from the student community which have received the GATE yesterday, GATE 2026. In fact, it was tough as compared to the GATE 2025 as such. So therefore, the cutoff definitely may go up, and if the students get above 55 to 60 marks, they are sure of getting a job in PSU. It is like that. So paper was definitely tough as compared to the last year. I would rate it as a moderate to the tough. So in this video, I am going to discuss in detail about the questions what I have received from the student community based upon their memory, because paper is not out, therefore they keep sending me the questions, whatever the data that is available in their mind. So I would like to discuss the paper in detail based upon the stream wise. First I will consider the thermal and fluid, then I will consider the applied mechanics and design, and then I consider the manufacturing and industrial. In fact, then I asked the students, why do you feel the paper was tough? Because they said some questions are very, very lengthy. They require a lot of time to perform. Even the best students, they would require the more time to complete the question in a stipulated time. Actually, because that is why I would rate it as a lengthy paper rather than the tough paper. Particularly, there are questions in the thermodynamics like the properties of pure substances. One question was given, it was definitely lengthy question. Then if you just look at the manufacturing, they has given the deep drawing question. Actually, that is also lengthier question. Question concept is easy, but to do the problem, to apply the formula and to solve the solution, and it will take definitely for a long time, even for a well prepared student. That is why I would rate this paper as tough. Tough doesn't mean that he has given a very critical concepts. Concepts were easy only, but the students may take a more time to complete the solution or to get the correct answer. That is why I rate it as the tough paper. Moderate to tough I could call it as. And in fact, all the three streams were given the equal weightage. Applied thermodynamics and that fluid mechanics heat transfer part has given around 25 to 26 marks, and production has got around 24 marks, and production and industrial, and the applied mechanics and design also approximately around 24 to 25. And the remaining, as you know, that 28 marks for the aptitude and general English and as well as the mathematics. Mathematics seems to be a moderate, actually not very tough. But engineering portion, I can definitely say it is slightly above moderate. I will rate it between the moderate and the tough. Now let me take the questions one by one. First I will consider the thermal stream. In the thermal stream, we have got the four subjects: fluid mechanics, heat transfer, thermodynamics, and applied thermodynamics, or the power plant engineering. So in in this part, as you expected, heat transfer was given the 8 marks. 8 marks questions actually. And I would like to tell you, in the overall, most of the questions are from the MCQ and NET type. There was not even a single question from the multiple selective questions. Multiple answer, no, multiple selective. That question, there is not even a single question. Last year also, GATE 25 also, there was only one question of MSQ. Whereas in this GATE 2026, there is no single question from the MSQ type. Multiple selective, no, there will be more than one answer. That there is not even a single question on the MSQ. All the questions are MCQ or NET type. Most of the 2 marks questions are coming in the NET model. That is, we have to type the answer. And most of the questions, 1 mark questions came from the MCQ model. Okay, so this is the overall pattern of the GATE 2026. Now I will consider each stream one by one and we will discuss the paper. First, let me go with the thermal stream. Thermodynamics, they are asked about 5 questions in the thermodynamics. An ideal gas is state 1, it brings to state 2 and state 3. Both end states 2 and 3 are on the same isotherm. That means same temperature, isotherm in the sense same temperature, temperature is constant. If P and H are the pressure and enthalpy respectively, then choose the correct statements. Actually, the whole concept of this question is lying only in single word called ideal gas, also known as the perfect gas. What is the main character of the ideal gas or the perfect gas? Air is considered to be an ideal gas. What is the main character of that? It will follows the PV is equal to MRT at all pressures and temperatures. Not only that, the main character of the ideal gas is its internal energy and as well as enthalpy depend only on the temperature. So many times I have repeated that concept in my videos, okay, in my class notes also. For ideal gas, the main thing is, what we have to notice here is, for ideal gas, both internal energy, U is a function of temperature, the precise function is like this, CV into T, and also the enthalpy, and which is the sum of U plus PV. It is also a function of temperature. Obviously, when U is a function of temperature, PV is equal to MRT. That means in this whole function, there is only, the whole thing will become a function of temperature, because U is already a function of temperature, PV is equal to MRT. That is the equation followed by the, ideal gas equation. Therefore, U plus PV would also be only a function of temperature. That means for ideal gas, both internal energy and enthalpy depend only on the temperature. Precisely, that function is like this. Okay, CV into T, and this is Cp into T. So the question goes like this. There is an isotherm. How do the isotherm appear on the PV plane? This is the isotherm, right? Isothermal curve. So that state 2 and state 3, that means supposing one ideal gas is beginning at state 1. In one process it may be coming like this, in another process it may be going like this. Finally, if this is 2 and this is 3, he is comparing between state 2 and state 3, whether the pressure is same or volume is same or the enthalpy is same. That is what he is asking, because 2 and 3, T2 is equal to T3 he has given. That means as long as the temperature is constant, the enthalpy also would be the constant. Therefore, H2 is equal to H3. This is the answer for this solution. C is the answer. See, beginning at state 1, the ideal gas is undergoing two different processes. One may be going like this, one may be going like this. We don't know what would be that processes, but we always know that at the end of the one process, that is state 2, at the end of the other process, that is state 3, both are on the same isotherm, constant temperature. So because T2 is equal to T3 as very clearly given in the problem, H2 will be equal to the H3, because enthalpy depends only on the temperature of the gas, for the ideal gas only, not for the real gas. For the real gas, enthalpy depends not only on the temperature but also on the pressure. That point you have to clearly observe this. So the question is, see, very straight question. Only thing what you have to notice, ideal gas, you have to identify that particular statement. Immediately we should strike in mind that yes, Joule's law. Actually, this is more precisely called as Joule's law of ideal gas. U is a function of temperature only. This is also precisely known as Joule's law of ideal gas. Going to the next question. In an isothermal process, net heat transfer is equal to net work transfer. We all know that actually. Isothermal process means constant temperature process. If you write the first law of thermodynamics, delta Q minus delta W is equal to du. du is equal to 0. du is equal to 0 if temperature is constant. Therefore, delta Q is equal to delta W. Or that means heat supplied is equal to work done by the gas, or heat rejected from the gas is equal to work done on the gas. They are not only equal in magnitude but also have the same sign. If heat is supplied to the gas isothermally, all that heat will be completely converted into the work, expansion work. If you are doing work on this gas isothermally, that means when the work done is negative, when we do the work on the system, it is considered as a negative. Heat must have to be rejected. I mean to say that in isothermal process, heat transfer is equal to work transfer, not only in magnitude but also in sign, which is indicated as a curve like this, PV, right? Maybe expansion or compression. It could be even isothermal compression also. In either way, work is equal to heat. This is a compression, this is expansion, right? Now the question goes like this: is the process possible? The process is not possible. It violates the first law of thermodynamics. It does not violate the first law of thermodynamics. What is first law of thermodynamics? Law of conservation of energy. Energy can neither be created nor destroyed, because it is only telling that heat and work are two different forms of energies which are just equal. Okay, so it is not violating the first law because it is not creating any energy. It is not generating any energy. It is a law of conservation of energy. Generally, people may think that the process is not possible as it violates the second law. In the second law of thermodynamics, particularly in the Kelvin-Planck statement, it is stated that all the heat can never be completely converted into the work, provided the system undergoes a cyclic process. Kelvin-Planck statement is defined for the cyclic process, but here isothermal process is a non-cyclic. It is a non-cyclic, right? So in a non-cyclic process, it is very much possible that the process can be possible, but there is again reservations. Isothermal process is highly reversible, internally reversible process. There are so many things you can understand in the isothermal process. This process has got the lowest slope on the PV plane. Its slope will be minus P by V. It is very difficult to achieve, but it is not that unachievable. It is achievable, but it is highly idealized process. Highly idealized process, internally reversible process. That is the reason why isothermal process is only there in those reversible cycles like Carnot cycle, Stirling cycle and Ericsson cycle. I told you many times in my notes also. Isothermal process is something like a very idealized process which can be practically achievable because it undergoes very slow. Deadly slow process is isothermal process. That is why it is there only in those reversible cycles, Carnot, Stirling and Ericsson. Also in the reciprocating air compressors, what is the ideal most compression process? Isothermal process. Can you achieve it practically? Yes, you may achieve it. It is a limit to your imagination. It can be achievable. It does not violate first law, it does not violate second law. It can be achievable, but provided you have to proceed the process very slowly. Infinite slowness is the criteria for the isothermal process. So answer is the process is possible. It does not violate the second law. It does not violate the first law. It is very much there in the Carnot cycle. In the Carnot cycle, two processes are isothermal expansion and isothermal compression. There are two processes are there. But only thing is here isothermal process, work transfer is equal to the heat transfer, not only in magnitude but also in direction. Right? It is there only in the reversible cycles. Yes, this question is a very lengthy question. Actually, question is easy only. It is based upon the properties of pure substances. Properties of pure substances, or you can say properties of steam, we can rather say. One should have a thorough idea about the process, how to read the problem, how to read the properties from the table, then only you would be able to do the problem. So question goes like this: initially there is 5 kg of water. 5 kg of water means which is a mixture of liquid water and steam at 80 degrees Celsius. 80 degrees Celsius it is there initially. Then you started supplying heat. There is initially there is some part liquid, there is some part vapor. Try to understand the question first. Question is given like this. Initially there is a mixture of liquid plus vapor. Total mass of the mixture is 5 kg. There is some liquid. You started supplying, giving heat. It is a rigid vessel. It cannot change its volume. Therefore, volume is constant. Mass is also constant. Specific volume is volume by mass, that also would remain constant. So it is an isochoric process with a constant specific volume. Initial state, it is like this. If you just look at the PV, these are the constant dryness fraction lines. It is beginning with state 1. It's dry. He is supplying the heat. That means process will go upwards with a constant specific volume. This is the initial dryness fraction. This is the final dryness fraction. Okay. He is asking what is the change in the level of the liquid before heating and after heating, and how long you are heating? You are heating that mixture till the temperature reaches 130 degrees Celsius. Initially the temperature is 80 degrees Celsius. The saturation temperature is 80 degrees Celsius. You are heating that mixture until the temperature becomes 130 degrees Celsius, which can be indicated on the PV plane, like a vertical line, where you are observing that there is increase of dryness fraction. Definitely, because as you are supplying the heat, some of the liquid may get evaporated into the steam, resulting in the increase of dryness fraction. The question asked is very cleverly has asked the question. There is certain level of liquid initially. Definitely after the liquid evaporates, some part of the liquid is evaporating because you are supplying the heat. Some liquid water is getting evaporated and becoming steam. Then obviously the level of the liquid will decrease. He is asking what would be the drop in level of the liquid. Very lengthy question actually, seems to be big, because students, most of the students told me that they could not do it. First of all, they did not understand the question. You have to understand like this. There is already a level of liquid is there. As you have supplied the heat, some of the liquid will evaporate. What is the change in the level of the liquid in the container given the diameter? First of all, you have to frame the solution in your mind. How can you get the level of the liquid? Only when you know how much volume of the liquid is evaporated, then definitely we can calculate the drop, because decrease in the height into area will be the change in liquid volume. Initially some volume of the liquid is there. After some liquid is evaporated, finally there is some level of liquid is there. If you can get the change in the level of the liquid volume, definitely we can get the change in the height. Initially this height is there. After some liquid is evaporated, the level may going like this. So he is asking what is this depth. To get this drop in liquid level, first of all you have to calculate what is the liquid that has been evaporated, or you have to know what is the initial volume of the liquid, you have to know the final volume of the liquid. So to get that initial volume and to get the finite volume, first of all you should know what is the initial dryness fraction and what is the final dryness fraction. What is the initial dryness fraction has been given 0.1. So initial volume of the liquid, first of all I would like to calculate what is the initial volume of the liquid from the initial dryness fraction 0.1. Dryness fraction is, how do you define the dryness fraction? X is equal to mass of the vapor divided by mass of the liquid plus mass of the vapor. Okay. So if we can calculate, that is mass of the vapor divided by mass of the liquid plus mass of the vapor is 5. So if we can calculate the mass of the vapor, that 5 minus mass of the vapor is the mass of the liquid. Mass of the liquid into Vf. This has been given the Vf. This is a liquid specific volume. That will give the initial volume. But first I am trying to get what is the initial volume of the liquid before supplying the heat. For that one, if you are able to get the mass of the liquid, specific volume is volume by mass. So mass of the liquid into Vf will give what is the initial volume of the liquid. So what is X? This is 0.1. Initially X1, MB1, So that ML1 initially it will be 5 minus MB1. So I am trying to explain what is the logic behind that. Once you get the mass of the liquid initially, volume of the liquid, I am putting, volume of the liquid initially will be mass of the liquid initially, 1 means initial state, into specific volume of the liquid initially, that is at 80 degrees Celsius. That has been given. We can get this is the volume of the liquid initially. Got my point? Try to understand. If you know the dryness fraction, things are over. Mass of the vapor divided by total mass of the mixture, that is 5 kg has been given. I can get the mass of the vapor. Mass of the vapor, 5 minus that mass of the vapor initially will give the mass of the liquid initially. That mass of the liquid into Vf1 will give the volume of the liquid initially. Then coming to the final point, final dryness fraction, you don't know what is the final dryness fraction. How to get the final dryness fraction? I already said this process is a constant specific volume process. I have indicated also here. So look at this, it is a vertical line. So I can calculate to, now my question is to get dryness fraction x2 finally, that is at what temperature? Final temperature is 130, that is at saturation temperature of 130 degrees Celsius. I need to calculate the dryness fraction. For that I equate this V1 is equal to V2. Process is isochoric. Since process is isochoric process, that pure substance steam is undergoing a isochoric process or constant volume process. How to get the V1? Vf1 plus x1 into Vg minus Vg1 minus Vf1. All 1 means initial state, that is at 80 degrees Celsius should be equal to the Vf2 plus x2 into Vg2 minus Vf2, that is at 130 degrees Celsius saturation temperature. All these values are given in the table. In the table, you know, Vf4, Vg, this is state 1. I can say all this data is for the state 1. All this data is for the state 2. You can substitute all these values there and obtain the dryness fraction. Definitely it will be more than the initial dryness fraction. Because you can clearly see this PV diagram also. Dryness fraction values are increasing there. This is state 1. This is state 1. This is state 2. Dryness fraction values are increased. Naturally, you can expect that because some of the liquid is evaporating into the steam, obviously the dryness fraction value will increase for the mixture after heat supply. Okay, initially, the dryness fraction is 0.1. After supplying the heat and reaching the condition of 130 degrees Celsius, dryness fraction value will be definitely more. If I can get the dryness fraction value, the same procedure as how I got this liquid, same procedure I will follow. What is that procedure? X2 is equal to mv2 by total mass of the mixture, ml2 plus mv2, that is mv2 mass of the vapor at state 2 divided by 5 kg, from which you can calculate the mass of the vapor. After getting the mass of the vapor at state 2, from which you can get the mass of the liquid at state 2, that is 5 minus mass is same, total mass of the mixture, you will get the mass of the liquid after heat supply. Then volume of liquid after heat supply, volume of the liquid after heat supply will be mass of the liquid after heat supply into Vf2. This is the mass of the liquid after heat supply. Now we got already the mass of the liquid before heat supply. This is the mass of the liquid before heat supply. This is mass of liquid, not mass of liquid, volume of liquid before heat supply. Before heat supply, this is the volume of the liquid. Okay, mass of the liquid into specific volume at state 1. This is the volume of the liquid initially. Now we got the volume of the liquid finally. After heat supply, what is the volume of liquid? Therefore, change in level of water, change in level of liquid water in container is equal to change in liquid volume divided by area of cross section. Area of cross section which is given. What is the area of cross section? This has been given as pi by 4. D square diameter of the container was given in the figure. You may notice that it is 15 centimeter. So the change in level delta H, change in level of the water will be change in liquid mass of the volume of the liquid 1 minus volume of the liquid 2 finally after C plot divided by pi by 4 d square, so many meters, and the answer could be obtained in centimeters also, because once we do everything in meters based upon the what answer, because it is an NAT type, this such a lengthy question will be numerical answer type, you have to type the answer, definitely maybe answer may be asked in centimeters. Got my point? So your main entity is we have to focus upon what is the volume of the liquid initially before supplying the heat, what is the volume of the liquid finally after heat supply. If you can get those, divide with the area of cross section of the container, you will get the change in level, difference in liquid levels initially and finally, difference in liquid levels of water. Okay, so very good question, lengthy question definitely. Even the most topper student also, it may take a little bit more time, you may have to consume more time. You first of all have to think, frame the problem. Generally all the phone calls I have received from the student, nobody was able to do it actually. They were trying here and there, they were wasting time, and immediately they jump to the next question because they don't want to waste much time on by sticking to this particular question. So this is the concept of the problem. Okay. This is definitely a tough question. Once again I am explaining, actually initially there is some liquid level is there. After supplying the heat, the pressure will change, everything will, temperature may change, but specific volume remains constant from this logic. Volume of the container is constant, mass of the mixture is constant, therefore specific volume is volume by mass, that should be constant. Based upon this logic, I have calculated the dryness fraction after heating. What is this? Is dryness fraction, quality of steam after heating. Okay, so that is the main logic here. Once we get this dryness fraction, I can calculate the mass of the vapor after heat supply, then I can get the mass of the liquid. From the mass of the liquid and by multiplying with the specific volume of the liquid, I get the volume of liquid after heat supply. So definitely good question, lengthy question, checking your fundamental definitions of the specific volume, how to calculate the properties of the steam for a wet mixture, what is the meaning of the dryness fraction. So all the problem revolves around that, what is the dryness fraction of the definition, how to calculate the properties of the wet steam, and what is the nature of the thermodynamic process. It is a isochoric or constant volume heating of the steam, okay, where some of the liquid may get evaporated. Temperature rises, pressure rises, but only one property remains constant, it is a specific volume. That point you have to keep in mind. This is a question on exergy. I have received the data, but different people have given the different data, but question concept I would like to explain. There is water, mass of flow rate of water, but to calculate the mass flow rate of the water, he has given the density of the water, area of cross section by using the continuity equation, velocity, so many kg per second. Some initial temperature was given. Initial temperature is 25 degrees Celsius, and finally it is reached to final temperature will be 250 degrees Celsius. Okay, this is the continuity equation. From the continuity equation, we can calculate mass flow rate of the water. How much heat is supplied here? Heat supplied is equal to mCp, m dot Cp, heat supplied per second, because he has asked the rate of exergy. Rate of exergy is given in watts, rate means per second. So he has given the mass flow rate of the water, mass flow rate of water, and then final temperature and initial temperature. Therefore, heat supplied per second will be mass flow rate of the water into Cp of the water, T final minus T initial will give the what is the total heat you are supplying. Obviously in kilojoule per second, taking that Cp of the water is, we expected that is 4.187 kilojoule. Even if it doesn't give, you have to remember this kilojoule per kg Kelvin, you have to calculate the what is the rate of heat supply. But what he has asked is the exergy, rate of exergy. or available energy. We can also say exergy is another name of the rate of, exergy is the rate of available energy, will be heat supplied per second minus T naught into delta S of the universe per second. T naught is the ambient temperature. That ambient temperature we may take it as the 25 degrees Celsius, that is 298 Kelvin. Particularly whenever you are calculating the irreversibility or change in entropy of the universe, we have to keep the temperatures only in Kelvin. So what is the delta S of the universe? Delta S of the universe is delta S of the universe, it will be minus heat lost by universe, by surroundings, divided, because heat is losing, divided by temperature, plus m dot Cp log T final by T initial. In the last few years, I think 22, 23, 24, last 3-4 years, because I have been daily, every year I keep giving the solutions for the gate. My experience is gate is more than 28 years. So in the last 28 years, I have solved so many number of questions for the gate mechanical. So many, because that time gate model was different. Before gate was offline only up to 2013. From 2014 it is going on online. In all these 28 or 29 years of gate teaching experience, those days papers were tough. Definitely papers were tough. But the question on this available energy or irreversibility or unavailable energy, etc., exergy or energy or whatever it is, for the last 4-5 years it is missing. Generally, gate is a very typical examination. If one topic is definitely missing, definitely you may expect that question. Particularly sometimes for the last 2-3 years they may repeat. Sometimes he may completely come in a different direction. Tangentially may come and insert that part. This available energy concept he has not asked 22, 23, 24, 25 also. I have not seen in these last 3-4 years gate papers. This time he has come. So this delta S of the rate of entropy generation of the universe. Rate of entropy generation of the universe, thermodynamic universe. It can be calculated like this in kilojoule per second, Kelvin. So you have to calculate this mass flow rate, what is the rate of heat supply? Rate of heat supply to water minus T naught into delta S of the universe per second. That will give the, you just have to supply this. You have to substitute this one. Rate of entropy generation of the universe, we have to subtract from the rate of heat supply to get the rate of exergy in kilojoule per second. Okay. Delta S of the universe should be calculated as heat lost from heat supplied from the surroundings divided by ambient temperature in Kelvin, T naught in Kelvin, all temperatures in Kelvin. This final temperature and initial temperature also must be in Kelvin. This should be in Kelvin, this should be in Kelvin. Okay. Natural logarithm only. Cp of the water would be given 4.18. Mass flow rate of the water can be calculated from the continuity equation, rho into area of cross section into velocity, so many kg per second. So this is definitely consumes time. This also consumes time. I said in the initially also when I started this video, paper was easy only, but the question set was lengthy, and even the topper would consume more time. Because as you read the question, you have to get the concept into the mind, apply the formula, and use the calculator. All this time, all these things require time. So time management is the most. Some questions are direct. Actually, some production I have seen theorem machines also, particularly in the gears and all. Just read the question and put the answer. It may take around 10 to 15 seconds. Time saved there should be used for this such a type of a NET question. Definitely, question is lengthy on this exergy concept. Right. Next question will be, draw the TS diagram for the ideal regenerative Rankine cycle. There are certain different inputs are coming from the student feedback. Some are saying it is simple Rankine cycle, some are saying simple ideal regenerative cycle, because from the figure I can say, from the figure that liquid condensate, you just look at this. In the Rankine cycle or the steam power plant, what is the state of the water leaving the pump? That is a liquid water at boiler pressure. That is going to the turbine and then entering the boiler. So this part from the diagram, from this diagram we can say that it is a regeneration. Regeneration means transfer of heat within the cycle from high temperature to the low temperature. So many times in my videos I have said, the main purpose of providing the regeneration in any thermodynamic cycle is to improve the thermal efficiency. It is done in the Breton cycle, it is done in the Rankine cycle, wherever it is done the purpose is one, to improve the thermal efficiency of the cycle. Here the liquid water leaving the pump at boiler pressure, going to the turbine and picking up the heat from the steam and then getting heated up. First let me show the simple Rankine cycle, then you will understand what is the meaning of the regeneration. This is a simple Rankine cycle without superheating. I will just put the without superheating, because for simplicity I do not keep the superheating. That is the state of the steam entering the turbine is simple dry saturated. This is a simple Rankine cycle without superheating. Simple ideal Rankine cycle, okay, without any regeneration, no regeneration here. This is the heat supply in the boiler, this is the expansion in the turbine, this is the heat rejection in the condenser, this is the pumping, okay, pumping of the water. Now you said the regeneration, ideal regeneration. The purpose I already said, purpose of regeneration is to increase the thermal efficiency. That means which cycle has got the highest thermal efficiency? Carnot cycle. So if you see, this is a Rankine cycle. If you draw the Carnot cycle, I draw the Carnot cycle between the same pressure limits. Carnot cycle is simply a rectangle. This is the boiler pressure, this is the condenser pressure. This is the thing, right? See, the main difference between this Carnot cycle and this ideal Rankine cycle is, you are observing that in the Rankine cycle you are supplying the heat at different temperatures. See, but if not this during change of phase, at least during this particular part you are supplying heat at different temperatures to the water. That means while you are supplying the heat, the temperature of the water is increasing, feed water is increasing in the boiler. So that causes the irreversibility in the cycle, and thereby the Rankine cycle, ideal Rankine cycle efficiency is lesser than the Carnot cycle efficiency. This is the main loophole which makes us to provide this regeneration. Because the simple Rankine cycle has got the lesser efficiency than the Carnot cycle, I am compelled to provide the regeneration to approach the Carnot cycle. So I can say this is Carnotization of the Rankine cycle is called as the ideal regeneration. When you provide the ideal regeneration means the water leaving the feed pump, it is picking up the heat from the steam, it looks like this. See, it is only a twisted form of the Carnot cycle. If you provide the ideal regeneration in the Rankine cycle, the cycle looks like this. It is only a twisted form of the Carnot cycle. See, the steam is rejecting heat to the water. There is a heat transfer. Steam is rejecting heat to the water. The temperature of the water is increasing and the temperature of the steam is decreasing. Steam is doing work in the turbine. At the same time heating this feed water. See this. Steam is expanding in the turbine, doing work. At the same time it is transferring heat to the water. So that means the change in drop in entropy of the steam would be exactly equal to the rise in entropy of the water, making this a complete internal adjustment without any irreversibility. So this is something like an idealized model of the regeneration, which cannot be practically achievable. Nobody can practically follow that. Nobody can practically achieve this. That is why we go for the bleeding, 2 or 3 bleeding points. We bleed the steam. Now I will draw the bleeding. Supposing actual regenerative cycle looks like this. Actual regenerative cycle looks like this, where you do the bleeding of the steam. Steam is bled and mixed with the, this is the bleeding of steam, and mixed with the, directly mixed with the feed water coming from the pump, and this steam bled and this water will get mixed up and finally to get the saturated liquid. This is the practical or actual regenerative cycle. Practical or actual regenerative Rankine cycle, which is done. This is also very commonly asked. Regeneration has asked so many things. Exactly 1 month back I had given the one video, how to make use of this 1 month. There also I mentioned, if at all any question is asked in the Rankine cycle, they will first ask about the regeneration, because regeneration results in the increment of thermal efficiency. But this is a practical regenerative Rankine cycle. But the question is asked about the idealized Rankine cycle. This idealized regenerative Rankine cycle, ideal regenerative Rankine cycle, steam is expanding in the turbine, at the same time it is transferring heat to the water. So this water is picking up the heat. By the time the water enters the boiler, it is at the saturation temperature. So the remaining heat you are supplying isothermally, you are reaching the Carnot cycle. So this is something like a twisted form of the Rankine cycle, Carnotization of the Rankine cycle, wherein this simple Rankine cycle is made to approach the Carnot cycle. Therefore, this ideal regenerative Rankine cycle would have the same thermal efficiency as that of the Carnot. Thermal efficiency of the Carnot are same, but we cannot practically achieve it. At least we can approach it by providing this practical regeneration. This is the boiler pressure, this is the condenser pressure, this is the bleeding pressure. So any bleeding of the steam with practical regeneration will improve the efficiency. So the question will be, answer will be like this. This should be the most probable answer. Assuming that the TS diagram is asked for the ideal regenerative Rankine cycle, whose efficiency, ideal regenerative Rankine cycle will have the same efficiency as that of the Carnot cycle, because this is a Carnot, right? This is a Carnot, a rectangle. You slightly push it leftwards, you will exactly get this. Condensation, heating of water by using the steam. Look at this, put the arrow this. Look at this, heat transfer from the steam to the water, where the water gets heated up and the temperature of the steam is decreasing. Temperature of the steam is decreasing because steam is doing work and as well as transferring heat. So the change in entropy of the steam is exactly equal to the change in entropy of the water. Therefore, there is no entropy generated in the universe. This is because it is supposed to be happening completely reversibly. This is called as a reversible heat supply between the steam and the water, the twisted form of the Rankine cycle, so that it almost appears like a Carnot cycle. So this cycle and this cycle almost looks same. That is why their efficiencies are also equal, but it is impractical. Practically we cannot achieve this. But if we cannot achieve this, at least you may approach it like this. Like by providing the practical regenerative cycle with the bleeding, that is called as with the bleeding of steam. What is the meaning of bleeding of steam? You will extract the steam from the turbine. You will extract the steam from the turbine and mix with the feed water coming from the pump, so that hot steam is mixed with the water. The final combined mixture will be a saturated liquid. This is a saturated liquid water at condenser bleeding pressure, You may provide 2 or 3 bleeding points. Here I provide only one bleeding. You may keep 2 or 3 bleeding points like this. You may keep one more bleeding here, one more bleeding here. As you increase the more and more bleeding points, your efficiency also will improve. And if you provide infinite number of the bleeding points, then finally you may achieve this ideal regenerative Rankine cycle, which we cannot do practically. If you provide infinite bleeding points, with infinite open feed water heaters. Finally, you may achieve this ideal regenerative Rankine cycle whose efficiency is equal to that of the Carnot cycle. That is not practically feasible because you cannot provide infinite feed water heaters. So this is all about that regeneration. Very commonly expected. If you just look at the overall questions asked in the last 10-15 years of GATE, the maximum number of questions regarding the Rankine cycle are asked about the regeneration. Sometimes he may ask about the what is the mass of the steam bled. This is the mass of the steam bled. Sometimes this may be asked how much percentage of the steam is bled to heat the water. So the questions can be formed like this. Majority of the Rankine cycle questions come from this regeneration. You can see the earlier papers also. This is a question on the Rayleigh flow. Question on the Rayleigh flow. There are some students are telling the isothermal flow. Actually, this is highly unexpected topic. This topic comes under the compressible fluid flow. What do you mean by compressible fluid flow? Density is bound to change with pressure. Density is a function of pressure. Density is not constant. That is the meaning of the compressible fluid flow. In compressible fluid flow, there are three different things. That chances will. One is called as the fan of flow. What do you mean by fan of flow? It is an adiabatic flow with friction. Constant area duct. Adiabatic flow with friction. In constant area duct. No heat transfer. In constant area duct. Second thing will be Rayleigh flow. Named after the Lord Rayleigh flow. Here it is a constant area duct. Area is constant. No friction. Here no friction. But there is a heat supply. There may be a heat supply or there may be a heat rejection. There may be heat supply or heat can be rejected also. Third thing is the isothermal flow. Some people are getting confused between the isothermal flow and the Rayleigh flow. The main difference between isothermal flow and Rayleigh flow is here friction exists. Friction exists. Heat transfer also exists. Heat transfer also there. Heat transfer also exists. So in the fan of flow, there is no heat transfer. It is an adiabatic. Q is equal to 0. In the Rayleigh flow, the Q heat supply will be there, or sometimes heat rejection also may be there. I don't say that it is only supply. There may be heat rejection also. May be there. But no friction. Area is constant, no friction here. The main difference between isothermal flow and Rayleigh flow is here friction exists, here no friction. So that any frictional heating is compensated by the heat transfer in the case of the isothermal flow. But actually, that is why the question I kept the optionally. Maybe a Rayleigh flow, maybe a isothermal. Some people are giving some students are telling it is the isothermal flow. Some people are telling it is the Rayleigh flow. Suppose I take it as the isothermal flow. If the temperature is constant, mass flow rate is also, because constant area duct steady flow. Here, if the isothermal is constant, mass flow rate is constant, rho AV is constant. That means A is constant means rho into V is constant. Temperature is constant, P is decreasing. He has given P is in the question, P is decreasing. In the question, this is P2. P2 is lesser than P1. Pressure is decreasing. So when the pressure is decreasing, P by rho is RT. Okay. As see, when the P is decreasing, rho is equal to P by RT. when the pressure is decreasing, density also decreases. As P decreases, implies density also decreases. As the density decreases, to keep this product constant, velocity will increase. So here the velocity increases in the direction of the flow. In the direction of the flow, velocity increases. Particularly if it is Rayleigh flow. In the Rayleigh flow, if m is less than 1, subsonic flows, the flow will be approaching, velocity increases, pressure decreases. If the flow is Rayleigh flow, I am talking about Rayleigh flow. If flow approaches sonic, flow approaches sonic velocity, m will tend to be, the limiting Mach number will become 1. If the initial velocity is also supersonic, whether the flow is subsonic or supersonic initially, the flow finally approaches sonic flow here. Finally that flow would become sonic at the end of the pressure drops. If the flow is initially subsonic, velocity increases. If the flow is initially supersonic, velocity decreases. Okay. So there are so many combinations are there in this particular topic. The questions I am not able to get the clear cut feedback from the students regarding this question, because these memory based questions, these are all. I am discussing the questions based upon the data I received from the students. Okay. So if your answer will be definitely, if the flow is, if it is given, the initial flow is given as Mach number is less than 1, subsonic, definitely the V2, V exit here, V2 will be greater than V1. V exit is greater than V inlet. Velocity increases. Pressure is decreasing. Pressure is decreasing. As the pressure decreases, density decreases, because rho is equal to P by RT, there is an ideal gas. As the density decreases, to keep the rho V product constant, velocity will be increasing. That is taking it as an isothermal flow. Even if it is a Rayleigh flow, if the initial flow is given as subsonic, m is less than 1, m is the Mach number. If the Mach number, initial Mach number is less than 1, or if the flow is subsonic, definitely the velocity will be increasing, because at the end of the flow gets choked. By the time the Mach number will become 1, that is, flow tends to be sonic. From subsonic to the sonic means the velocity of the fluid will be increasing. Okay. So the question may be from the either Rayleigh flow or isothermal flow. Some students or some are discussing that Rayleigh flow and isothermal flow are same. No, they are absolutely not same. In the Rayleigh flow, there will not be any friction, but in isothermal flow, friction exists. So the frictional heating of the fluid is compensated by the heat transfer, keeping the temperature constant. All these things are applied in the combustion chamber designs and also in the heat exchangers. In the combustion chamber designs, all these concepts will be applicable, whereas fan air flow is completely an adiabatic, no heat transfer, but there is a friction, with friction, okay, where the stagnation temperature remains constant, because no heat transfer, stagnation temperature remains constant. T0 is the stagnation temperature. So taking this as an isothermal flow, my answer for this question will be velocity at the exit is more than the velocity at the inlet. Yes, this is a question on the heat transfer. Heat transfer, I think he has asked about 8 marks totally. One question came from the heat exchanger, as the student said. This is from the fins, a small topic in the conduction chapter. Surprisingly, there is one question in the radiation. I could not get the complete data from that. It is a tough question, radiation, some students are telling. There is one question from the heat exchangers, 2 questions from the conduction. The fins also part of the conduction. It is a long fin. It is a long fin. For a long fin, the rate of actually is comparing. For long fin, you have to note, you have to remember the infinitely long fin. The rate of heat transfer from the fin will be square root of Hp Ka T0 minus T infinity. Whereas T0 is the base temperature, very long fin. T0 is the base temperature. T infinity is the ambient temperature. H is the convection heat transfer coefficient. This P is the perimeter of the fin. P is the perimeter of the fin. A is the area of cross section of the fin. K is the thermal conductivity of the material. H is the convection heat transfer coefficient. This is the formula for calculating the, for infinitely long fin heat transfer rate, very long fin. Square root of HPKA T naught minus T infinity. T naught is the root temperature or base temperature. T infinity is the ambient temperature. P is the perimeter. P is the perimeter and A is the area of cross section of the fin. Area of cross section of the fin, right? So he is comparing, there are two different cross sections. One is square cross section and other is circular cross section. There are same dimensions, A is equal to D. One is D and D is equal to, right? So perimeter, this is a perimeter. This is the area of cross section. So he is comparing this thing for the same H, for the same K, same root temperature, same ambient temperature, only difference comes in the perimeter and the area of cross section. Very simple question only. That is H is same, T naught is same, T infinity is same, K is also same. It becomes root of P into A for the first, I think first is the square divided by root of P into A for the circular cross section. Yes, very easy question, that is P is the 4 into D, that is for the circular square, what is that perimeter? 4 into D square, because D into D it is square, divided by what is the perimeter for the circle? Pi by 4, perimeter will be pi D, area will be pi by 4 D square. Yes, it will directly give the answer. Assuming that same thermal conductivity for both the materials, for the circular cross section, and for one fin will be of circular cross section, one fin will be of the square cross section. He is comparing the rate of heat transfer for the square and the circular. Assuming that this diameter of the fin and the side of the square are remaining same, this will give the answer. Because K is same thermal conductivity, same convection heat transfer coefficient, same root temperature, same ambient temperature. What is different between this cross section and this cross section? Perimeters are different and area of cross section is different. Taking this dimension as D, I just took the ratio of the square versus circular for the root of PA. It is a very infinitely long fin. Generally, most of the fin cases you will get the insulated tip fin. That is generally fin questions don't appear commonly. In the entire last 26 years of GATE, I can say fin questions have come just 2 or 3 times, just 2 or maximum 2 or 3 times only from the last 25 years of GATE heat transfer. This time it has come, okay. So unexpectedly they may ask actually some not frequently asked topics, they may post in some of the GATE. That is why GATE is a very specialized and why people call it as a tough exam, toughest exam in the engineering. Why? Because very unexpectedly some questions may come suddenly and people are unprepared and they may be missing that question. Yeah, this is the question on the free convection. Free or natural convection. The question on the regarding the buoyancy forces, very simple. Supposing if there is a hot plate, if this is a hot plate exposed to the ambient air, definitely what is the pattern of the airflow in the free convection? This is the pattern of the airflow, because air picks up the heat. As the air picks up the heat, as the temperature of the air increases, the density decreases, air becomes lighter, the flow will tend to go up. Supposing if this same thing is a cold plate, and what will be the pattern of the airflow if it is a free convection? This is the pattern of the flow. This question has asked last year also, but last year is asked, last year same question but spherical. GATE 25, you can recall the pattern for the spherical is asked. So all this flow pattern is because of the buoyancy forces. The main driving forces for the flow in free or natural convection heat transfer is buoyancy forces, which are created by the density changes of the fluid. The main driving force for the flow of the fluid in free convection is change in density. Fluid expands or fluid contracts. Okay. Because of which density as the resulting because of the density changes of the fluid, because of the volume changes of the fluid, rather I can say, buoyancy forces come into action and they provide the flow. Like sometimes against the gravity, sometimes supported by the gravity. You can see there is a slab here T1, there is a T2. You see the velocity patterns, this is a velocity pattern. What is happening here? The flow is upwards. When the flow is upwards, definitely the fluid temperature in this domain, it will be, flow is going upwards. That means T3 should have been lesser than T1. When you come to this one here, fluid is getting down. That means fluid is losing heat. Heat transfer from the fluid to the plate. That means T3 should be greater than T2. Here T3 should be lesser than T1. See this. This is a hot plate, this is a cold plate. This is a fluid flow pattern due to the buoyancy forces or due to the density changes. As that, see, in this case, as the fluid gets the heat, its temperature increases, density decreases. As a result, as the density decreases, fluid becomes lighter. It tends to move up. Here the density is increasing because the temperature, fluid is losing heat, temperature of the fluid is decreasing, density is increasing. As the density of the fluid increases, it becomes heavier, it goes down. So the entire question pattern is purely regarding the buoyancy and density changes of the fluid. Same question asked in gate 25 exactly, but for the spherical cases regarding the G is downwards, acceleration due to gravity, but against the gravity the flow will happen. If this is a hot sphere, hot ball or hot sphere, the flow pattern will be like this. Got it? The question on the free convection, simple question. There is one question on the lumped heat analysis. They are given a spherical body some 400 degrees Celsius and the ambient temperature is given 20 degrees Celsius. A spherical ball is exposed to the fluid. The final temperature is somewhere around 50 degrees Celsius, I guess. Exactly, I don't remember the data. The radius size was given, and T infinity is 20 degrees Celsius. This is T infinity, and there is a heat transfer with a known convection heat transfer coefficient. Is asking to reach so and so final temperature, how much time is taken? How much time? Tau. Tau is the time in seconds. So for the last 2 to 3 years, there was no question on the lumped heat analysis. Unsteady state. This is called as the unsteady state heat conduction, where two numbers are important. What are the two dimensionless numbers? Biot number and Fourier number. Generally, these two are the important numbers we discuss in the unsteady state or transient heat conduction. So lumped heat, assuming that Biot number is less than 0.1, if it is a metallic body, lumped heat analysis is valid. Lumped heat analysis is valid. In the last month video also had given what are the topics we have to revise properly. This is one topic I mentioned very clearly. Lumped heat analysis valid since the Biot number is less than 0.1. This is a criteria to apply this lumped heat analysis. What do you mean by lumped heat analysis? There are no internal temperature gradients. There are no internal temperature differences at any instant of time. The whole body temperature is decreasing with the time uniformly. So no internal temperature gradients, entire body is at a uniform temperature, same temperature. So that is called as the lumped heat analysis, for which this formula is valid. Ti minus T infinity divided by T minus T infinity is equal to e to the power of HA by rho V Cp into tau. Tau is the time, from which you can calculate the time in seconds. This is a concept of the problem. V is A by V. A by V is the surface area divided by volume. It becomes 3 by R for the spherical body. For the sphere, 3 by R. A radius should have been given. It is a very regular and very commonly asked question. In the last 3-4 years, they have not been asking, but before that, it was regularly being asked. Gate 18, 17, 19, like that. If you see, it was regularly asked a pattern question, but last 2-3 years, the question is not, this model is not appearing. Suddenly, this year it has come. Okay, you just get the time taken for the ball to reach final temperature of 50 degrees Celsius. Actually, the values I don't remember exactly based upon the student feedback. This is a question I have framed it. Time in seconds to reach this final temperature. Once the body is exposed to the fluid ambient temperature and give it a given H value, convection heat transfer coefficient, A by V is 3 by R. Only precaution is the Cp we have to keep in joule per kg Kelvin. The specific heat you have to maintain in joule per kg. There is a question on the counterflow heat exchanger, that is regarding the very typical pattern, actually lengthy question. It is also lengthy question. He has given the hot fluid inlet temperature, hot fluid exit temperature, cold fluid inlet temperature, cold fluid exit temperature, from which we have to calculate delta Ti and delta Te, and by using the LMTD formula, delta Ti minus delta Te divided by ln delta Ti by delta Te, we have to get the LMTD, from which we have to calculate UA delta Ti. Because he has given the pipe, he has given the diameters and he has given the thickness also. He has given the thickness of the pipes also, that K, and this is the diameters Di, or rather we can say Ri. This is Ri, this is Ro, outer radius, thermal conductivity given, internal convection heat transfer coefficient given, outside convection heat transfer given. This is a lengthy question. First of all, you have to get the overall heat transfer coefficient based upon the inside area, 1 by Hi plus Ri by K into log Ro by Ri plus Ri by Ro into 1 by HO. Hi and HO are the convection heat transfer coefficient on inside and outside, and LMTD. This is LMTD, delta Tm. You can calculate the heat transfer rate between hot and cold fluids. Your main question is to calculate this overall heat transfer coefficient. Internal heat transfer area will be pi di L, so many meter square. Okay. So this is the main question on the counterflow heat exchanger, lengthy LMTD model. If you are given the heat transfer rate, you can calculate the area. In this case, because you are given the diameter and length, you can calculate the area of the heat transfer, that is pi di into L, and then calculate the heat transfer rate in watts. Only precaution here is UI you have to calculate overall heat transfer coefficient, you have to calculate carefully. Definitely a lengthy question, so many watt per meter square Kelvin. Right, then comes the, then I will do the fluid mechanics. I will finish the some questions are very simple in the fluid mechanics. Bernoulli's equation. First thing is, what is the, where the Bernoulli's equation cannot be applied and it can be applied. We should know what are the assumptions based upon the Bernoulli's equation, and where it can be applied, where it cannot be applied, you should know that. Generally, when you are deriving the Bernoulli's equation, actually how it is derived? By integrating the Euler's equation of motion. By integrating Euler's equation of motion, right? How did you obtain the Bernoulli's? By integrating the Euler's equation. Incidentally, Euler and Bernoulli are contemporary. Euler is a student of Bernoulli actually. Leonard Euler and Daniel Bernoulli, they are the stalwarts in the fluid mechanics. When deriving the Euler's equation, the main assumption is flow is irrotational or inviscid or potential. Inviscid flow. Generally, assumptions are flow is steady, flow is irrotational flow. That means the fluid masses, while translating in the flow, they do not rotate about their mean centers. Inviscid or inviscid flow. Inviscid, there are no viscous forces. Incompressible flow. With these assumptions, Bernoulli's equation has been derived. That means we consider only two forces. One is body force and the other is pressure force. For deriving the Bernoulli's equation or from the integrating the Euler's equation, we assume that there are only two forces that are acting over the fluid element in motion. Number one, pressure force. We consider only pressure force and gravity force. No viscous force. No viscous force, no shear force. Viscous is a shear, right? No viscous force. So that is one assumption, and based on which you get P by rho plus V square by 2G plus ZZ is equal to constant, or simply P by W plus V square by 2. Sorry, this is a mistake. Yeah, now it's right. Or P by W plus V square by 2G plus Z is equal to constant just by dividing with the G. Okay, rho G is W, specific weight. But this Bernoulli's equation, this constant of integration, C will be defined for the Bernoulli's equation if you take the two streamlines. If the flow is irrotational, you can apply between any 2 points in the flow. If a flow is irrotational, Bernoulli's equation can be applied between any 2 points in the flow. Any 2 points. No restriction. Because the constants of integration is same for this streamline and for this streamline. For this streamline, the constant of integration is same. But if the flow is irrotational, if flow is rotational, Bernoulli's equation can be applied Bernoulli's equation cannot be applied between 2 points, between 2 locations, lying on 2 different streamlines. Okay, supposing if this is one streamline, if this is streamline, this C1, this is streamline 1, this is streamline 2. So the constant of integration is different for this streamline. You cannot write between this point and if the flow is rotational. That point you cannot write the Bernoulli's equation between these 2 points if the flow is rotational. If the flow is irrotational, no problem, because you can write this point between these 2 points also. We can write if the flow is irrotational flow. The other name of the irrotational flow is potential flow, because the velocity potential function phi exists only for the irrotational flow. Surprisingly, there is not a much weightage for the FM for the kinematics in this particular. Kinematics, they didn't ask anything, because I was expecting a question from the stream function or velocity potential or acceleration components of the fluid or equation of the streamline, flow net, etc., continuity equation, but there is no question. Very surprisingly, generally very rarely they miss the question from the kinematics of the fluid flow. They missed here. So that question paper is definitely unusual in this year as compared to the regular patterns. So this is one question, and another question will be fluid mechanics. There is a bend in the horizontal plane. There is a pipe bend. In horizontal plane. So he is asking the pressure on the inner side, this is Pi, and the pressure on the outer side is given here, where the pressure will be more. The flow is like this, the flow is happening like this, where the pressure of the fluid will be more, inner side or outer side. So the question can be answered if you know this flow of the fluid in the pipe bend is a free vortex flow. It is free vortex flow. What do you mean by free vortex flow? The flow of the fluid in any circular path without any external torque imposed on the fluid. The flow of the fluid in a whirlpool, there is a free vortex flow. The flow of the fluid in a pipe bend is a free vortex, like in case of the spiral casing of the centrifugal pump. In the centrifugal pump, there is a volute casing. There is a volute casing or a spiral casing surrounding the impeller. What is the flow of the fluid in that spiral casing or the volute casing? In the centrifugal pump, the flow is free vortex flow. During the free vortex flow, no external torque is applied. The equation of the flow will be V into R is equal to constant. So if you just look at this radius of curvature, this is RO, here it is Ri, okay. V is inversely proportional to the radius. As here the radius is more, therefore velocity is lesser. That is where streamlines are diverging. When the velocity is lesser, from the Bernoulli's equation, pressure will be more. Okay, PO will be V at the outer radius is more. Sorry, outer radius is lesser. Outer radius is lesser. When the V at the outer radius is lesser, definitely pressure will be more. From the Bernoulli's equation, PO will be greater than Pi. You can use the concept of the centripetal force also. Centripetal force, or rather the pressure at this location will be more than the pressure at the inner one. And here the velocity being lesser, the streamlines are diverging here, and here the streamlines are converging. So basically the flow is free vortex flow, because the radius of curvature is more here, velocity at the outer radius is lesser, velocity of the streamlines here is lesser as compared to the velocity of the streamlines here, velocity of the flow here. As such, from the Bernoulli's equation, here the pressure is more, pressure at the outer surface, outer curve is more than at the inner curve, PO is greater than Pi. Then the one question is given from the pressure measurement. The question was somewhat typical. There is one container. There is one container to which a pressure gauge is attached. This container has got, there is inclined pipe was kept like this, which is carrying some piston. There is some weight is acting, some mass is acting. Or you can consider the mass of the piston itself, certain mass. Obviously it has got weight. This is all fluid. He is asking the area of the piston was given. Area of the piston was given. So if you just draw the free body diagram for the piston, this is the free body diagram for the piston. So the weight will be acting like this, and the weight component, he has given this angle also. I think this angle is theta. Theta is 30 degrees, something is given. The weight component will be exactly balanced by the fluid pressure force exerted by the fluid. Okay. That means for equilibrium for static equilibrium of piston, that mg component of weight downwards, should be equal to pressure force exerted by the fluid. What is the component of the weight? mg sin theta, okay, should be equal to the gauge pressure. I am not taking the absolute pressure because already there is an atmospheric pressure here. But if you want the gauge, there is a gauge. Any gauge pressure, what do you mean by gauge? Any pressure which is more than the atmospheric is called as a gauge pressure. I am considering the atmospheric pressure is not there because I am not considering, actually there is atmospheric pressure. Is acting. But any pressure more than the atmospheric is a gauge. I am just calculating the gauge pressure into pi by 4 d square, where d is the diameter of the piston. Okay. So that will give the gauge pressure from which the weight component m into mass into g, no, that is m into g, that component, its component will be acting like this. Look at this. This is the weight component. Mg means this is mg sin theta downwards is balanced by the pressure force, pressure into area, from which you can calculate the gauge pressure. Pascal's law also applies. The pressure exerted at a point is distributed uniformly in all the directions. Actually, there is slight ambiguity also here. Supposing if the height of the container is more, this is somewhere handling here, you will get at the same elevation. But above this, if it is a mercury, in this direction the pressure keeps increasing. But actually I am taking this as a gas whose density is negligibly small. So the change in pressure with elevation is neglected within the fluid. Within the fluid, the change in pressure with elevation is neglected. Supposing if it is a mercury, say for example, it is a heavy liquid, this elevation is given. Supposing if he is measuring somewhere here, you should be given this height also. And because that elevation of the liquid also will matter in the difference of pressure. Got my point? Supposing if it is a gas, doesn't matter. But if it is a mercury, very heavy density liquid, even 2 mm distance, vertical distance also will matter a lot in causing the difference of pressure. Suppose if it is a mercury, you get a different pressure here, you get a different pressure here, you get a different pressure here, because as you go to greater and higher elevations, pressure will decrease. So in such case, we have to take that elevation also into account. At what height is this and what is the difference, where you have kept the gauge, everything will matter. But here something like a gas you may consider, where the density is low. The changes in pressure with elevation are neglected within this container. Got it? So the concept is the pressure force that is exerted over here, is exactly balancing the weight component. So that is the there is one more question also people are telling regarding the momentum equation, impulse momentum equation. That is one more question also there, but I did not get the complete details about that question. Some momentum equation, one question is also being asked. Okay. But surprisingly, the kinematics missed in this. I don't know actually why they skipped that. Usually kinematics part is a very important part. Rarely they miss in the gate examination. This gate, nothing is asked in the kinematics regarding velocity, potential, stream function, equation of the streamline, or acceleration components, or continuity equation, differential equation, differential continuity equation in the differential form, the divergent V, divergent V is equal to 0, curl V, that irrotationality condition, irrotational, rotational. So all these concepts very rarely they skip. But this year gate, surprisingly there is no much question. I don't know exact, some students they did not give me any feedback because these are all the memory based questions. Based upon the vague data what we receive from the student community, I am presenting the key and solutions. Okay. This is about regarding the fluid machinery also. There is one question, one reaction turbine question, one reaction turbine, reaction turbine maybe Francis. Reaction turbine means immediately what we may get is mind is Francis turbine. The inlet velocity triangle, one question, it seems they have asked. I did not get the complete details. Inlet velocity triangle, there is one question as asked, that is hydro reaction turbine, that is the Francis turbine. And one question is missing, that is in the momentum equation or impulse momentum equation application. There is a strength of materials, next part. So, a simply supported beam of cross section 20 centimeters may be mm, actually this I really doubt they are centimeters, it should be mm. Point C is at neutral layer in the simply supported beam. Find the load P if the shear stress at C is 3 MPa. In the cross section of the beam at the neutral axis, there will be a neutral axis, right? The point C is at the neutral axis. Okay, what that shear for stress is mega, find you have to calculate the load P. So this can be calculated. First of all, what will be the shear force, because shear force here, average shear force at C can be calculated by noting the reactions there. This is RA, this is RB, taking sigma MB is equal to 0, RA into, I just want to know, calculate what is the reaction at A. RA into 3 plus 2, 5 is equal to P into moments about the P into 3, right? RA will be equal to 3 P by 5. This is the reaction at A, vertical reaction at A. Therefore, the shear force at C will be 3P by 5. Shear stress, average shear stress at C, at that section where the C is there, will be equal to the 3P by 5 into area of cross section. What is the area of cross section? This is 20 by 45, right? This is 20, this is mm, right? 20 by 45, that is 20 by 1000 into 45 by 1000, area of cross section, right? Force divided by area is the stress. But generally at this cross section, you get an average, but this at the C we get the one point, that maximum shear stress at the neutral axis will be 1.5 times the average stress. Shear stress at C, that is neutral axis, will be equal to the 1.5 times the average shear stress, that is 1.5 times the 3P by 5 into 20 into 45 divided by 10 power 6, because I am converting into the meter there. So this, because this is the tau max, that is at the shear, because at the neutral axis here. But what you calculated is the average shear stress. 1.5 times more is the shear stress at C. That is given as 3 megapascal, 3 into 10 power 6, 10 cube kilopascal. So from which you can calculate the load P in kilonewtons, because this has been given, that maximum shear stress that is at the neutral axis has been given in the value as 3 megapascal, converted into the kilopascal. So you will get the load P. I just calculated the reaction RA. the shear force at C will be the shear force at C will be the reaction RA, and that shear force divided by the area of cross section will give the average shear stress. Average shear stress into 1.5 will give the maximum shear stress what we see at the neutral axis, because very clearly has given that C is at the neutral axis, neutral layer. Okay. After getting that maximum shear stress which you are seeing at the neutral layer, equate that to the 3 megapascal, you will get the load P. Load P will be 2,666.7 newtons. Based upon the data I received, I calculated this. Yes, this is we have to calculate the shear force and bending moment diagram. This is a couple, bending couple on the simply supported beam. Actually, by looking at this, the shear force diagram, it can, because shear force SFD will be beginning, shear force will be beginning from here only. This cannot be the answer. This cannot be the answer. This is SFD. This cannot be the answer. This cannot be the answer. Answer can be either this or this, because both are same. Looking at the bending moment there, looking at the bending moment here, what is the bending moment here? PL by 2 into PL by 2. Here the bending moment obviously will be 0. Here the bending moment is 0. Bending moment is 0 only here. So only here bending moment is 0. So answer will be B. You don't have to calculate anything. This BMD cannot be possible. What is the bending moment at the fixed end? L by 2 anti-clockwise, P into L by 2 clockwise. Both will cancel. Bending moment will be 0 here. So answer will be, this is PL by 2 up to here, up to this point, and beyond that bending moment keeps decreasing, it becomes 0 at the fixed end. So answer is B. Straight. This some questions seem to be very simple actually. Totally there are 5 to 6 questions are asked in the strength of materials, all seem to be simple. Last time design was asked more, strength of materials lesser. This time strength of materials and machine design put together has asked around 8 marks. Strength of materials and machine design put together has asked about 8 marks. Out of which one question is theories of failure, that is common between strength of materials and machine design, because that is where the theories of failure, in the last video I had given exactly 1 month back, what to do in the last 1 month preparation, very clearly I was mentioning the theories of failure. That too specifically I mentioned von Mises theory, maximum distortion energy theory, that is asked here. Last year also is asked von Mises theory, because that theory is very important, usually applied for the ductile materials like steel and aluminum. Maximum distortion energy theory. There is one question on that, I will do that. So totally if you look at the strength of materials and machine design, he has asked around 8 questions, out of which 5 to 6 are from the strength of materials and 2 or 3 from the machine design. That is the overall weightage for the SOM and MD combined. Okay. This is a very simple question regarding the shear force and bending moment diagram. Very simple. Answer is B. This is the SFD. This is the BMD. You can directly see bending moment here is 0. This is PL by 2 anti-clockwise. This P into L by 2, PL by 2. Both will cancel. Bending moment is 0 here. But in all the rest of the figures, there is some bending moment given. So directly we can go to the question. See, elimination way, we can say we don't have to calculate any reactions and all. Directly we can go to the answers. This is a overhang beams there. There is a one hinge given. For the given internally hinged beam configuration, determine the reaction at support C. One important thing what you have to notice is at the hinge D, bending moment is 0. That is the one important thing. At the hinge, that is D, bending moment is 0. So if we just take this part of the beam, there is one reaction RA here. First you have to calculate the reactions, right? This is RA here, this is RC here, we have to calculate. There is RB here. So RA for this part, if you take the bending moment sigma m about d 0, that is RA into 1 should be equal to the 10 into 0.5, 10 into 0.5. So we got the RA. Once we got RA, then sigma MB is equal to 0. Okay, sigma about this point. Okay, from which we can calculate RA into 0.5 plus 0.5 plus 0.2. Here, RA is how much you got? 5 kilonewtons. Okay, when this is 5, this is 10. So obviously here the reaction at D will be, vertical reaction at D will be 5. This is 5 for this part of the beam. So once you get this, this will become RD, right? So when this is 5, take the moments about the B, you will get the RC as 5 kilonewtons. There is 25 external load is there. Take the moments about B, that is 25 clockwise into 0.2, and this 5 into 0.2 should be equal to the RC into 0.2 plus 0.6 plus 0.2, 0.8. You will get the RC as 5 kilonewtons. It is an overhang beam. The main thing is at the hinge the bending moment is 0. That you can say point of counterflexure, we can also say. A square plate of dimension 1 meter by is welded along the diagonal. Ratio of the normal stress to shear stress on the plane normal to the weld. This one, this angle is 90 degrees. On the plane normal to the weld. By looking at the angle, this is given as 45 degrees. This angle will be 90. This will be 45 degrees, obviously anti-clockwise. On this plane, what is the normal stress? What is the shear stress? That ratio we have to get. We know the normal stress formula, sigma x, this is sigma x compressive, this is sigma y, sigma x plus sigma y by 2 plus sigma x sigma y by 2 cos 2 theta plus tau xy sin 2 theta. Here there is no tau, there is no shear stress. There is no tau acting here, tau is equal to 0. So there are only two biaxial stresses. Cos 2 theta is 90, put theta as, this is sigma x. We want on this plane, put theta as 45 degrees minus, you can keep, because you are going in the anti-clockwise sense. So if you get sigma n, normal stress will be, this is cos 90 is 0, okay. So it becomes 6.5 plus 25 divided by 2 megapascal. This is the normal stress. This one we got as the 9.25 megapascal. And come to the shear stress, tau at theta is equal to minus 45 on this plane I am talking about, this plane. He is asked, this is a weld, he is asking on the plane normal to that weld, this is a weld, right. On this plane what is the shear stress he is asking, that is sigma x minus sigma y by 2. sigma x minus sigma y by 2 sine 2 theta. Tau is anyhow is 0 minus tau xy cos 2 theta. Anyhow this tau is not there. So we have the half into, I am putting the, sorry, this will become minus because it is a compressive, no? This will become a minus sign, this is a plus sign. Half into minus 6.5 minus 2.5 into minus 1. So it will become the ratio will be sigma normal by tau, that is shear, it will be 0.587. We got the normal stress, we got the shear stress. This is the shear stress on that plane at 90 degrees to the weld. Actually this point also I mentioned very clearly. This is the basis for drawing the Mohr circle also. Principal stresses, principal strains, Mohr circle, these biaxial stresses are very, very important. Every gate exam they will ask, every gate exam. Last year also he has asked, this year also he has asked. Very simple only, not a good thing, but one should be careful about the angle, sign. Why I have kept a negative sign here? Because it is of compressive. Why I have kept a positive sign here? Because if it is of tensile, there is no shear here. There is no, but tau xy is 0. So this component automatically this will become 0. He didn't give. Sometimes he will give the shear also. Sometimes he will give the shear. But in this question there is no shear shear force acting, shear stress acting on that plane. Okay, there are only two normal stresses. One is of compressive nature, one is of tensile. We need to calculate the normal stress on that plane at 90 degrees to the weld, and also the shear. We have to get the ratio. Direct formula we can use the formula. It's just substitute in the formula and take the ratio. Direct question only, not at all a difficult question. Luckily this year strength of materials questions are easy, moderate I can say, not easy, moderate, not tough, not at all tough. So this is regarding the maximum distortion energy theory. Maximum distortion energy theory. Which is also called as the von Mises theory. Usually applied for the ductile materials like mild steel and the aluminum. In the maximum, this is here the is not SYS, and this is yield stress under tensile test. This is given as 550 MPa. From von Mises theory, we know that sigma 1 square plus sigma 2 square minus sigma 1 sigma 2 will be SYT by factor of safety whole square. This is the von Mises theory, from which we can calculate the sigma as 103.94 megapascal. Direct application of the von Mises. Same question, similar question as asked in gate 25 also. Yield stress under the tensile test. It is applicable for the ductile materials, very most famous theory, ductile materials. This von Mises theory or the maximum distortion energy theory is applicable, like aluminum, steel. This is the criteria. And this is also again asked on the pressure vessel, thin cylinders. The question on the thin cylinder. There is a thin cylinder with the diameter d and thickness t, subject to the fluid pressure P. He is asking the what is the hoop, he has given the hoop strain, maximum allowable strain on the surface, that is a hoop strain. Hoop strain is given as 0.00034. This is a pressure, fluid pressure. Direct application of the formula, hoop strain is given as PD by 4T into Young's modulus 2 minus mu, where mu is the Poisson's ratio. Where mu is the Poisson's ratio. Just substitute here, you will get the pressure as 840 kilopascal. Maximum strain is the hoop strain. Okay. Thin cylinder questions are PD by 2T, PD, well, two formulae, longitudinal stress and longitudinal strain. PD by 2T, PD by 4T. Thick cylinder they have never asked. Always whenever the question comes, that comes from the thin cylinders only. So, strength of materials questions are quite easy this time. All the 5-6 questions are quite easy, not a much difficult. Generally he has missed the strain energy concepts like that. Usually strain energy also, that resilience, proof for resilience, modulus of resilience or strain energy, they are the most likely topics to be asked, but this time they didn't touch. So paper was a little bit unusual, that is why many students are rating it as a tough, because they expected something differently paper came. That is why GATE is a difficult exam, people think, because many times it may go against your expectations. See, radiation generally they will never miss. I think one question is there in the radiation heat transfer, but I never, students are not able to give me the feedback. One question is there, radiation. If you can tell me that, I will be grateful. If you can WhatsApp to me. Just check there. Is it buffering there? Okay. Right. With this strength of materials is over. Then coming to the machine design. Machine design has asked only two questions there. One on the spring, one on the welded joint. Design of the welded joints. This is L. A plate is joined using a double parallel fillet weld and subject to the load P. The maximum permissible shear stress is tau allowed. Welding leg size is H and weld length is L. Then the maximum permissible load is. Actually, in that question there is some ambiguity. If this figure is given, if this is noted as L, you will get one option. If this L is not there, if you take this total length of the weld as L, you will get a different answer. So question is somewhat, if you take this as L, you will get option B. If you take this total portion as the L, you will get the option A. Students must be wise enough to, if the figure is given, people should be very, very careful. Because the formula for the P, load P will be taking this as a L. I am talking this as L. L is given, assuming that 0.707 H into L into tau allowable stress, from which answer will be B. Not all, this is allowed, maximum allowable stress. If this length is not given, if the L is not given, if you take this as L, total thing as L, answer will be A. Is the design of welded joints. Question on the design of welded joints. Then he has given the question on the helical spring. Load is P. T is the diameter. This is d by 2 is the radius. Now, he is asking the maximum value of shear stress at the wire cross section. Maximum shear stress will be sum of two things. One is direct stress, that is force by area, plus torsional shearing stress. Torsional shear stress. Direct stress will be how much? Force by area. Torsional shear stress will be 16T by pi d cube. Torque T is equal to force into d by 2 radius. Okay, that is F divided by pi by 4 d square. This is a direct stress. 16 into F into d by 2 divided by pi d cube. Answer will be A. This is a load, right? There is a direct shear stress will be there. And apart from that, there is a torsional shear stress will be. Direct shear stress plus torsional shear stress. Torsional shear stress will be T 16 into T. Torque will be torsion, no? Torque will be F twisting moment. We can rather say twisting moment. Torque or the twisting moment. We can say this is the twisting moment. Twisting moment will be F into d by 2, where d is the total diameter of the radius, whereas small d is the diameter of the wire. This is the small d, whereas capital D is the diameter of that helical spring as such. Okay, answer is A. Both the machine design questions are very simple as such. Then comes the theory of machines. I will do the theory of machines and engineering mechanics. Now I will do the theory of machines here. There is an arm. In that arm, there is some particle is moving, sliding with a velocity. This arm angular velocity is omega. Is asking the Coriolis component of acceleration. Coriolis component of acceleration will be 2 into v sliding into omega. One insect is sliding with a velocity v. Velocity over the sliding, this is 0.2. This arm is having an angular velocity about this axis as with a omega of 3. This is 0.2. Then what will be the Coriolis component of acceleration is given by 2 into v sliding into omega. Answer will be 2 into 0.2 into 3. That will be the Coriolis component of acceleration. Then this is the gyroscopic couple. Regarding the gyroscopic couple, there is a velocity has been given, velocity of the flight, there may be a flight, there may be a flight velocity has been given, and moment of inertia, mass moment of inertia given 1 kg meter square. It is taking a turn, it is taking a turn of with a radius of curvature 2000 meters. It is a flight. A flight is moving with a velocity v and with a mass moment of inertia 1 kg per meter square, and the radius of curvature of the flight turning is 2000 meters. Okay. Then what is the turning? What is the turning, that I mean angular velocity of the turning? That will be v by r. Velocity divided by the radius of curvature. Omega is given 2 pi 1 by 60. That gyroscopic couple will be I omega p. You will get the C. Very unexpected question. Gyroscope recently he did not ask, but it's very simple, straight formula. He didn't is asking whether the flight is moving up or fluid is going down. That direction also he didn't ask. Straight he has given, straight application of the formula I omega p. Mass moment of inertia given, and radius of curvature is given, from which omega p of the turning can be obtained, v by r, and omega the rotation is given 2 pi n by 60 angular velocity. I omega p is the formula for the gyroscopic couple. Straight question. Now this is the damping coefficient is given, critical damping coefficient is given, find the logarithmic decrement. Direct formula based. This direct formula based. There is no nothing to there we have to just calculate damping ratio. Theory of machines questions, they are straightforward this year. The zeta will be C by Cc, 35 by 350, it is 0.1. Logarithmic decrement will be 2 pi zeta divided by 1 minus zeta square. It will be 0.6314. The straight formula based question in the theory of machines. Straight. Actually, strength of materials and theory of machines this year, in that particular, they are straightforward. They don't consume much time. They don't consume time at all. Some questions, you see, some questions are consuming a lot of time. Particularly, I had already done properties of pure substances. I will see in one in the forming also. It is a time consuming question. I will do that now. Now this is the logarithmic decrement. Which gear is idler? That idler gear is that one which is connected on the left side and right side. This is the only gear 4, right? Gear 4 is connected on the left and right, on left side and right side. That is why gear 4 is the idler gear. See, if you just look at the 3 on the right side, 1 on the right side, 5 on the left side, okay, 2 on the left side only. So only 4 is connected on both right side and left side, that is a idler gear. Worm gear is used neither parallel nor intersecting shaft. This is the answer. Worm gear is used neither parallel nor intersecting. So this is the question, little bit engineering mechanics, straight question only. He is asking minimum mass m that would be just preventing the slide. Minimum mass. Minimum mass means that is minimum mass, if you putting the more, that will prevent the sliding. But that means the frictional force, because it is tending to slide downwards, friction force will be upwards. It is just holding that block. So if you just draw the free body diagram for that, okay, this is 50 kg. This will be 50 kg means 50 g newtons, everything I will do the newtons. 50 g sin 30, 50 g cos 30. Engineering mechanics question, this is 50 g cos 30. This is 50 kg, 50 g sin 30, and therefore the normal reaction will be 50 g cos 30. Okay, here this is a frictionless pulley. This will be tensioned here, M, this will be M. This will be same, frictionless pulley, this will be M. So this will be 2 mg. You just equate that, this is a friction because it is tending, since block is just about to slide downwards, friction force will be upwards. Is just on the verge, limiting, that is mu into Rn. This is upwards, this is mg 50 g cos 30, that is 50. Just write the equation of motion. Just when the block is just about to slide, when the block is just about to slide, write the equation of motion, that is, write the equation of equilibrium, that is downwards will, how many forces are there downwards? This is 50 g sin 30, this 50 g sin 30 should be equal to friction and mu into normal reaction. Normal reaction will be 50 g cos 30 plus 2 into m into g. G may get cancelled, you will get the m value directly in kg. I think 6 kg gets that. You have to this is mg. This is mg, it will be mg here. That mg will be transferred here and here, because that is mg, this is mg, that will becomes 2 mg. The force here exactly will be 2 mg. The force here exactly will be 2 mg. This is mg, this is mg, that will be 2 mg here in this chord. This is 2 mg, this is a normal reaction, this is a frictional force is upwards because the block is just about to slide down. That means frictional force is upwards. How many forces are acting here? 50 g sin 30, frictional force upwards, 2 mg upwards. Simple question, inclined plane. These kind of questions very easily would have done in IIT coachings or JEE, etc. These kind of problems. Inclined plane with friction. Very simple question in engineering mechanics. So this is another question there. There is a ladder. There is a ladder to the wall like this. This is A, this is B. This A is sliding downwards with 6 meters per second. Then what is the velocity at the center of gravity G, at the midpoint? This is L. Total distance is L. This will be L by 2, this will be L by 2. What will be the velocity for the G is asked. Okay, this problem can be solved by using the instantaneous center, IC. This IC is obtained, instantaneous center, I. instantaneous center, and just join this instantaneous center with the center of gravity, and this everything is 45, this is 45, this is 45, everything is 45, right. Sin 45 Vg by Va, Vg will be Va by Va sin 45, this will be 4.24. Direct question based upon the instantaneous center method. The instantaneous center for this A and B are obtained like this. This is the instantaneous center, and if you join that one with the center of gravity, this is L by 2, this is L by 2, total distance is L. You take the, this is Vg, this is Va, this is Vg. So, Va by Vg, Vg by Va will be the sin 45. Everything is, this is this is 45, this is 45, this is L by 2, because this is a center of gravity. And this can be done by using the relative velocity method also. At point O, by using the relative velocity method also it can be done. This is relative to the, for the A, this is Vg, this is B is horizontal, and this will be the midpoint will be the G. So this will be the Vg. This is 6, this is 45, this is 90 degrees. We can easily calculate by using the relative velocity method. Either way it can be doing. We can do it by relative velocity method or instantaneous center method. That is easy, straight. Instantaneous center method is straight. He has given a ladder. This point A is sliding downwards with 6 meters per second. Then what will be the velocity of the midpoint of the ladder? This is B, B is moving like this, A is moving like this. So engineering mechanics, he has given only 2 questions, this one and the previous inclined plane. This is also quite easy. This is a friction, just you have to apply the law of friction. Force of friction will be equal to the mu into Rn. This weight of 50 kg has been divided into 2 components. One is 50 g cos 30. Weight will be 50 g downwards. 50 g cos 30, 50 g sin 30. That is the components of this weight. This is normal reaction will be 50 g cos 30. Force of friction will be mu into Rn. Mu is given. Mu has been given there 0.2, from which you can calculate, because this upward force will be 2 into mg. It is not mg. Supposing if the block is connected like this, it will be only mg. Now it is not like this. Pulley over pulley. Therefore, it will be mg here, 2 mg it becomes. Same question. That well, this is given as 6. What will be the velocity of the midpoint? Same question. Now the engineering material science, so the question is there. He has given the density, face centered cube, FCC metal as a density there, atomic weight is given, Avogadro number is given, find the atomic radius in mm. Density will be equal to average number of atoms in FCC into, this is a formula, atomic weight, only one question in the material science, divided by Avogadro's number into volume of the unit cell. This is the volume of unit cell. One question in the material science, from which you will get the R. But yes, you will get in centimeter, because this is rho is atomic weight is given as gram per mole. Density is given as 2.6 2.71 into 10 grams per centimeter cube. So we will get the answer in centimeter there, but he has given the nanometer. 1 centimeter, see the units are very important. Nanometer, this is 1 cm is equal to 10 power 7 nanometer. So we have to give the answer in nanometer. Atomic radius in, not in mm, sorry, it is nm. Nm means nanometer. Only one question asked in the engineering, not mechanics, sorry, engineering materials or material science. Usually only one question will come in the gate in the material science, only one question. Only one will be expected, particularly where if it is an IES exam, they will ask around 10 questions they will ask, the IES prelims there. There it is very important. But in gate always they may ask one or sometimes they may not ask. Next question is regarding the orthogonal turning. I told you exactly 1 month back, I clearly said there will be definitely one question in the orthogonal turning or orthogonal metal cutting, orthogonal turning operation. Every time, this is a question on the merchant circle, merchant analysis. Mechanics of metal cutting, which is also called all merchant circle or merchant analysis. Look at the video I had given exactly 1 month back. Exactly 1 month back I said what are the important topics you have to refer again and again in this 1 month. This topic I mentioned, question has come. See that. During orthogonal, by using a single point cutting tool, feed rate is given, the uncut chip thickness was given, the shear angle is given, tangential force component and radial force components are given, value of the shear force is. From merchant analysis, value of the shear force is given by tangential force component, where theta is the shear angle, radial force component, radial or axial thrust, radial or axial into sin theta, where theta is given as what is the tangential force component, he has given 800, this is cos 20 minus 150 sin 20, this will be 700.45 newtons. The shear force will be where Fc is the tangential force, F radial, no, this will be radial thrust or radial thrust or axial thrust also you can say, because there are 3 mutually perpendicular directions, one is tangential, one is radial, another is axial. This is the Fc is the tangential force component, this is the F radial will be the radial force component. Both are given, theta is the shear angle, this is theta. For the milling operation, not the mailing, it is the Jiction fixtures there, milling fixture height has been asked, it should be more than the 205. There is only one option, that is 210. Because when the miller should not touch the fixture there, so it should be there must be some clearance here. When you are there must be some clearance provided. This is a total depth of cut, and that should be that fixture, that the suitable value of the fixture should be height of the fixture should be more than this depth of cutting. That there is only one value more than the 205, that is 210. See, this is again a question that was repeated. Taylor's two-life equation. Generally, Taylor's two-life equation is V2 to the power of n is equal to constant. Last year also, this question was asked. In the last month, 1 month back video I had given, very clearly mentioned this, look into that equation. But in the earlier papers, they have given about the other machining operations. Here is asked about the drilling operation. For drilling operation, this Taylor's true life equation will take the form of N is the RPMs there. N1 is given as 200, N2 is given as 300, 2 life, T is a 2 life. 2 life in drilling operation, 2 life in drilling operation will be number of holes drilled into L by Sn. This is the machining time for each hole. This is the machining time for each hole. So, if you substitute that one there, RPMs are given 200 into 150 into L by S into 200 whole to the power of n, where n is the exponent of the Taylor's true life equation. 300 into 60 holes you have done, L by S into 300 whole to the power of n. You take the logarithms there, L by S gets cancelled there. This gets cancelled, and you will get the n value as 0.30. So the exponent in the Taylor's true life equation will be 0.306. This so many times this Taylor's true life equation problem is so many times in the GATE examination was asked. Last year also asked, GATE 2005 also, GATE 2025 also is asked, and this year also. But the way they ask the question will be different, but the basic equation that has to be used in solving the problem is Taylor's true life equation. In deep drying operation of a rectangular, is a forming 30% stretching in length and 15% reduction in thickness. Assume volume to be constant. The normal anisotropy of the sheet metal is. First we have to get what is the true strain along the length direction, true strain along the width direction, true strain along the thickness direction, and the total volumetric strain will be the sum of the strains in the 3 mutually perpendicular directions: strain in the length, strain in the width, and strain in the thickness. First let me calculate true strain in the length direction. True strain in length direction. Logarithm length final by length initial. He has given the percentage change in the length, logarithm 30% stretching in length, that is ln 1.3 L initial by L initial, ln 1.3, it will be 0.2623. This will get cancelled. Again the strain in the thickness direction, strain along the thickness direction, strain along thickness direction, ln thickness, final thickness divided by initial thickness, ln what is the final thickness? Only 15% reduction, that means 0.85 T initial divided by T initial. Logarithm of less than 1 will be negative. Negative only shows that it is a getting reduced, minus 0.1625, it getting compressed, right? Reduction, minus sign only shows that thickness is getting reduced. So volumetric strain, because the total volume is constant, volumetric strain is 0. Volumetric strain is 0, that is the strain along the length direction plus strain along the width direction plus strain along the thickness direction, right. So that therefore the strain along the width direction, you get it as strain in width direction, you get from this equation strain in width direction as minus 0.0988. This is also getting, minus sign only shows that width is also getting reduced. Here the minus sign shows that thickness also getting reduced, only the length is increasing. So normal anisotropy will be the ratio of the strain in the width direction divided by strain in the thickness direction. Normal anisotropy strain in the width direction divided by strain in the thickness direction. This will be 0.608. Slightly lengthy question, but concept is straightforward, but slightly lengthy calculation part. This part in the of the product manufacturing, that is manufacturing is actually that not many number of questions appeared in the manufacturing. Only 7, turning 1, metrology instrumentation, and drilling 1, and jigs and fixtures 1. And casting defects, there is one question was there. There is one question in the casting defects. Casting defects, one question he has asked. Actually, there may be dross or the scar or the swell and scab. They actually, the last class also had very clearly said in the last month discussion of the video what to prepare one month. All the topics I mentioned in that video exactly 1 month back I had given, they are repeated. In the casting, the most commonly asked question will be solidification time, number 1. This time he has not come. This time he has asked the casting defects. If this is missing, they will ask about the casting solidification time. This time he has not asked that. Last time he has asked. Okay. This is already done, this question. The value of 5 peaks. Manufacturing has given RZ average over definite ordinate sigma of the peak minus sigma of the values divided by 5, center line average value. CLA, sigma of the peak plus sigma of the valley divided by 10. Both of them are getting the more or less same answer. You will getting approximately 4.57 answer here. Here the answer will be missing facets. This is additive manufacturing. Question on the additive manufacturing, answer will be D. Now the industrial questions, I had given the 4 questions only. This is a question on the EOQ. Direct formula substitution. Economic order quantity inventory Q star 2D CO by CH. CH will be 0.5 into 12 for the 12 months. It is 1354. In the industrial engineering, most commonly asked question will be in EOQ, economic order quantity, in the inventory. This is on the simplex method, but very rarely these questions will be asked generally. You have to convert. This is a question on the simplex method. This is the forecasting. This is the 4 questions is asked in the industrial engineering. Demand of a certain commodity are given. If the smoothing effect coefficient is 0.7, then the forecast for the month of March will be. Then it is a CPM PET, Program Evolution Review Technique, critical path method, and answer will be 22. We have to construct the critical path. Actually 4 questions only. I think my industrial engineering has asked only 4. In fact, mathematics we are able to obtain only the 4 questions we are able to obtain. This is integration. This is a differential equations, 1 question has come. Newton-Raphson method 1 is given, that is pertaining to the Taylor series. Linear algebra, he didn't give any question there. That is usually expected, but this time is missing. I already said this paper is a little bit unusual. Unexpected questions have come. The expected questions have not appeared here. This is a general aptitude. Only few questions only we are able to get from the students. This is an English. English you get the answer is B. The incident that has happened, that an animal has fallen into a pit, and the animal is an elephant. It is very surprised to see that the elephant is in the pain for miserable, as it has to look for the crowd. The team scored 250 runs in 20 overs despite the rainy day. English also seemed to be quite easy this time. English and aptitude seem to be quite easy. That 28 marks, 15 marks of general and verbal aptitude and 13 marks of mathematics. If you are able to score that part, you are should able to score more. Because engineering paper has come a little bit tougher. If you could compensate that by scoring more in the general aptitude and the verbal English and also the mathematics. Mathematics part, I heard that mathematics is a bit easier only, not very tough. But the engineering stream for the 72 marks paper has come definitely moderate to tougher level. It is not easy paper definitely. As compared to the 25, it is tough. And compared to 24 also, the paper seems to be a bit lengthy. Strength of materials questions are quite easy. Theory of machines also not tough, but heat transfer is somewhat tougher only, I can say, particularly that heat exchange problem. Not tough in the sense it's a lengthy paper. The student must be able to spend more time in calculating the answer. So as such, overall, if you student able to get more than 55, 60 is a very good score, very good score, I can say. If your score is somewhere between 35 to 45, very reasonably good. If you are getting above 50 means you are entering into some good IIT, I can say. If you are getting more than 50, 55 marks, 50 marks above, you will be damn sure of getting a good, very good NIT or IIT MTech seat. If you are scoring about above 65, you are sure of getting a job in a PSU. So that way overall the cutoff may go a little bit more this year because of the moderate to toughness of the paper. So that is what a general thing which I am hearing from the students. So with this I would like to conclude the paper analysis and discussion of the GATE 2026. This is Sekhar from M Sigma Gokulam, and any doubts pertaining to your this paper, you may call me or you can WhatsApp to me. If you want to have any discussion about the paper and the question there, some questions are missing there, particularly that fluid machinery one question is missing, one radiation question I could not get proper data. But otherwise, most of the questions we are able to catch up with the students and able to get the feedback from the students. Paper is definitely rating is moderate to tough. Okay. With this, all the best. Good luck, my dear students. Wish you the best for your future. Bye.